Good morning, good afternoon, good evening, wherever you are. Thanks for staying tuned and thanks for following up in the previous videos. Now, this will be the third video on solar home sizing, that is on the energy audit. And today we'll be going to size a PV module. And when I talk about PV module, interchangeably we use it as solar module. Understand the word PV. We use solar module and the word module to uh, interchangeably is used as maybe panel. You get it. So now we're going to size a PV module, that is maybe a solar panel. How to determine the number of PVs that you need, the number of solar panel that you need when you are designing your system, maybe for residential or commercial or for industry. That is commercial industry, we mean by C and I. So now this one will give us an insight on what to do. Maybe you are connecting your solar panel in parallel, maybe you are connecting your solar panel in series. So it will give you the knowledge what you need to do no matter the amount. But these are just the basics and the foundations. And I believe that we have some large solar farms. How do you do those ones? We have uh, software for those ones that make it very easy. You understand? Ready-made software, because you can't be calculating and calculating and calculating. You understand? But this one is just for the knowledge of it, so that you will know that okay, you can't just go to the market and say I need 150 watt and need 250 watt and you run into problem. But if you know the basics, it will guide you a lot. So, and then I believe you've watched the first video where we do our energy audit, because we'll be using all these answers. Let me say the parameters, that is the energy daily. We'll be using it till the end of our design. Then the wattage, then the number of batteries we got. That was the last video. That was the second video when we sized our battery. All these data will be needed as we progress. So let's move ahead. Now, these are the steps to sizing a PV module. The steps to size a PV module. This is the formula we will be using, and that's our solar array size is equal to the E daily, that is the average energy daily, over inverter efficiency times PSH and times PPR. Remember that in the first table, we got our total energy daily to be 1930 watt hour. That is our E daily. That is the total energy that the client want to consume. That's it. And remember that the total power too, if you look at the table, the total power is equal to, I think, 325 watt. That's the total power. And when we were designing our battery, remember that we got the capacity of the battery that is needed is 3574 amp hour. That's the capacity of the battery. And we discovered that after we considered the number of battery we need in series, the number of battery we need in parallel, we discovered that we said we will need a total number of 2 batteries, that is 12 volts 220 Ah being the battery we selected, but the two numbers will be connected in parallel so that we get this. Yeah, so let's take note of this data: 1, 2, and then 3, because we'll make use of them. So back to how to size our Back to how to size our solar array. E daily. Remember, I told us that our E daily is 1930 watt hour. That is 1.93 kilowatt hour. That's it. That's the energy, average energy consumed daily by the client. And the inverter efficiency. In our inverter efficiency, we use 0.9. Then, what do we mean by this PSH? The peak sun hours. You know, according to different locations, for instance, in my country, we have different locations. We have the northern part, we have the southern part, we have the western part, and different number of hours. We experience different number of hours as which the rate at which the sun shines. Yes, the rate of sun shines per day differs. Are you getting it? And that's what we mean by the PSH. That is peak sun hours. How many hours do you experience sunshine in a day? Are you getting it? So the PSH is the number of hours per day when solar irradiance. You know, when we call that irradiance. Do you understand? The solar in the solar world we call it irradiance. That is the number of hours per day when solar irradiance averages 1000 watts per square meter. 1000 when it averages 1000 watts, that is 1 kilowatt per square meter. That's what we mean by the peak sun hours. And in a different form, number of hours you experience sunlight in a day. Let's leave it like that. Number of hours you experience sunshine in a day. And sometimes some people will say, the sun has been shining since morning. It's more than 8 hours. Sometimes it depends. You don't even need too much sun. Do you understand? For your system to be fully charged, you don't even need too much sun, because too much the rate, let me put it this way, that if your sun is too hot, if the radiance is too hot, it affects your system. How? Because all these solar modules, they are tested. They are something we call STC, standard test condition, and all these modules are tested at 25 degrees Celsius. And if your sun, the sun reaches, maybe the temperature reaches like maybe 30 degrees Celsius, 36 degrees Celsius. In some areas, it even goes as high as maybe 40 degrees Celsius. So it affects the efficiency of your system. The higher the temperature, the lower the voltage that is supplied. So sometimes you don't need too much temperature for your system to perform optimally. Do you get it? Because all these things, the solar modules, you will see it at the back. There's something we call nameplate. You will see it at the back. STC, 25 degrees Celsius. So if something is tested with 25 degrees Celsius, how do you want it to perform best at 30 degrees Celsius or at 28 degrees Celsius? It will still perform, but the efficiency will be lower. So that's just it. So the peak sun hours, you understand? Averagely, how many hours do you experience sunshine in a day? That's it. Then the panel performance ratio. A panel cannot supply its wattage, its full wattage. It cannot work maximum at 100%. Do you get it? It cannot work maximum at 100%. So we rate it that a panel can at least supply 65% of its rated power. Do you understand? 65%. That's what we mean by panel performance ratio. And why can the panel not supply up to 100%? It's due to one, temperature. Temperature is part of it. Then temperature, I just made mention of temperature. Temperature is part of it. Then shading. Maybe where you are installing, maybe you have trees all around, or maybe you are installing in a bungalow, maybe on the rooftop bungalow. Then you have an high-rise building that will cast shadow. All these things, are you getting it? All these parameters affect the rate at which a panel will perform. Then the system inefficiency too. The system inefficiency, maybe due to design. Are you getting it? Maybe due to design. All these parameters can affect the performance of your panel. So you don't expect your panel to perform at maximum power. You understand, at 100%. And that's why it's good to lower your efficiency. Let me put it that way. So agreeably, we discovered that, okay, let's put it this way, that your panel will deliver 65%. Do you understand? It will deliver 65%. So it means if you have a 1000 watt panel, by 65% will be 0.65. So you are saying the panel will supply only 650 watts. Are you getting it? Temperature, shading, system inefficiency, losses due to cabling. Do you understand? Because you are going to cable it. So another one is losses. There will be losses before it delivers. You understand? To your inverter. So all these are factored in. So for a 1000 watts maybe array, you discover that it may not be able to supply, for a premium panel, it may not be able to supply more than 65%. Thank you. So we're moving ahead. So I was talking about sizing, you understand, peak on hours. For example, in Nigeria, we have the mangrove swamp. Peak sun hours for the mangrove swamp averagely is 4 hours. And those areas are maybe Port Harcourt, Delta, maybe Bayelsa, you getting the high rainforest 4.5 like Ekiti, maybe the southwest. Yeah, maybe the southwest, Osun, maybe Lagos. Are you getting it? So Guinea Savannah, 5 hours. Benue, Kaduna, maybe FCT, the Kogi, the Middle Belt. Then the Sudan Savannah, maybe 5 hours. Kano, Katsina, those places in the northern side, they experience more peak sun hours than in the southwest. Then the Sahara Savannah, Borno, Bauchi, like that. Are you getting it? So averagely peak sun hours. So when you are designing, you just pick any of it and design. But if you are not maybe within Nigeria, you will have your own peak sun hours. You get it. So that's just it. So now steps to sizing a PV module. Having the formula solar array size, are you getting it? Watts in wattage is equal to E daily over inverter efficiency times PSH. Now I told you earlier that the PSH means peak sun hours. How many hours you experience sunshine in a day averagely. And the PPR is panel performance ratio, that you are not expected your panel to deliver its maximum power. You get it? It cannot deliver its maximum power, and unanimously we agree that okay, 65%, it will deliver 65% of its power. So now 1930 watts, which is our energy daily. From the first video we made on our design, yes, energy audit, that's our E daily, that is the watt hour to be consumed, the energy to be consumed by the client, and our inverter efficiency is 0.9. And because of where we are, you understand, we choose 4.5 as our PSH. That is, I experience 4.5 hours a day of sunshine. Then our panel performance ratio is 0.65. 65% means 65 divided by 100, which is 0.65. So that's it. Then doing this, multiplying it out using our calculator, we get this. So the hour, we can cross out the hour. So this one we get 733.14 watts peak. We call it peak wattage. You understand? That's it. And remember, we can get something like maybe 733.14 panel. Are you getting it? It's not, panels are not rated like that. And so we just have to, like, okay, approximate up to be 750, and I can decide that okay, I will use 800 watt peak. Do you understand? But you don't undersize. You don't say let me choose 700. No, that would be a great mistake. Are you getting it? You need to be up. You understand? So from this, we have some things we call 12-volt panel. We have 12-volt panel. We have 24-volt panel. Yeah, and we have some too, 48-volt panel. Yeah, we have that. Yeah. So 12-volt panel, usually, if you have like 18 volts, it can charge your system. Are you getting it? 12-volt panel, usually, you will see them, you will see their VOC. By the time we go ahead, you will understand what I mean by VOC, VIMP, IMP. And every panel has a nameplate. Are you getting it? So panels like maybe 100 watts to even up to 200 watts, most of them are 12-volt panel. But above 200 watts, maybe like 250 to 300 to 350, most of them are 24-volt panel. Are you getting it? So we have panels like from now to from 100 watts, we have 150 watts, we have 180 watts, we have 190 watts. We have presently, we have some high rated panel of 720 watts, single panel. And these ones are more 48-volt system or more 48-volt panel because their VOC is higher, some to 50, you understand, 50, 55 volts. Hope you got it. So now we are going to determine how many panels now do I need. Do you understand? For this 750, I can decide to say, okay, I can decide to say 150. I can decide to say I need 150 watts panel. So 150 watts panel, I think by 5, 150 watt panel will be 0, will be 5, 750. So it means I will need maybe 5. Do you understand? I can decide to say, okay, let me up my game. Let me get a 200 watts. 200 watts. Are you getting it? So if I get a 200 watts, it means I will need 4 to make 800. Are you getting it? So it now depends on your connection. Do you get the explanation? So let's move forward. Now, so number of solar panels, that's what we want to get. I've decided that, okay, I am using a 750 watt panel. Okay, no, 750 watts is what we got. Are you getting it? That's the requirement to charge our system efficiently. Now, I now say, okay, I'm going for 190 watt panel. It's only 190 watt panel that is available. Do you understand? So the 750, that's the total size of the array. Are you getting it? That you want to use. Okay, now you now determine which panel do you want to go for, how many. So the number of solar panels now will be 750 divided by 190. I choose 190. Are you getting it? That's the panel I want to use. So 750 divided by 190 will now give me 3.94 solar panels. So I can't get 3.94 solar panel. The 0.94, I can't get it in the market. So I need to up it. So it means I need 4 units. Are you getting it? Yeah? Of 190 watt solar panel. 4 units of 190 watt solar panel. That's what I need for my system. So now there's something we call nameplate. This is the nameplate of the solar panel I want to use. Every solar panel has a nameplate, and this is the nameplate. You can see maximum power. The maximum power, is P max equals to 190 watts. That's the maximum power it can deliver. Do you understand? And the VMP equals to 20.85 volts. The BMP is the maximum voltage, is the voltage at the maximum power, the voltage at this maximum power. And this IMP, which is 9.11A, that's the current at the maximum power. The current the panel will deliver at 190 watts. That's the current at maximum power. Then the VOC, which is 24.8 volts. The VOC means open circuit voltage. The OC there means open circuit voltage. And what do we mean by this open circuit voltage? It means if you put your digital meter or your analog meter, all this the panel has two probes, negative and positive. It means at no load, when you have not connected the panel to anything, you should read this voltage. If the panel is facing the sun, you should read this voltage. Then the ISC, which is 9.66A, means short circuit current. I means current, short circuit. That it means if you have your clamp meter, if you now connect positive and negative together, are you getting it? If you bring it together and using your clamp meter around the cable, this is the maximum current that is allowed to flow. And that for is short duration, because if you connect it for a longer duration, it might damage the panel. Do you understand? So that's just the basic explanation. And if you now multiply this together, it should give you approximately 190. That is the voltage at maximum power and the current at maximum power. It will give you that. So now we've discovered that we need 4 units of 190 watts. Then how do you now connect it? And remember that remember that also remember that we need 4 units of 190 watts. And remember that our battery capacity, which is chosen, is 12 volts, 220 Ah, and to be connected in parallel. Are you getting it? We got our battery capacity is 357.4, if I'm not mistaken. That's the battery capacity. But we need 220 amps, 2 units of 220 amps, so that we'll be able to get this 357. So if we connect 2 units of 220 amps in parallel, we'll sum the capacity. It means 220 Ah plus 220 Ah, which will give us 440 Ah, if my calculation is right, which is above this. Yeah, 440 Ah. Do you understand? So at that, how do we now connect our 4 units of 190 watts? We have controllers, 2 types of controllers. We have PWM and we have MPPT. PWM means pulse width modulation. Are you getting it? And the MPPT means maximum power point. And the MPPT, maximum power point tracker. And the MPPT is the most efficient one. You can connect your let me say panels in parallel and series, and intelligently the MPPT will do justice to any of the connections, but you can't do that on PWM. Apart from the PWM is not efficient, it works. Apart from that is not efficient, it wastes energy. But the MPPT will track the maximum power you need to charge your system. So, for instance, now I need 4 units, and you equally need a good current. Do you understand? To manage your system very well. You need a good current to manage your system very well. And that's why when you are choosing your panel too, you must choose your panel. You must choose a good panel. Do you understand? You must choose a good panel. So now it now depends if I'm using PWM. For instance, if I'm using an MPPT, and remember that our system is 12-volt system. Yeah, our system is 12-volt system, but because of the capacity and because of our load, do you understand? Because of our load, that's why we are using 2 batteries in parallel. So now this is how I want to connect. I'm using an MPPT. I'm using an MPPT controller. So my panels, this is the parameter. My panels, I want it to go like this. I want to connect my panels in parallel. And when you are connecting in parallel, it means positive to positive to positive to positive, negative to negative to negative to negative. That's parallel connection. So this is my panel. This is 1. This is 2. This is 3. This is 4. Yeah, yeah. This is the objective symbol for solar panel. And remember, this is the positive side, this is the positive side, this is the positive side, this is the positive side. And then okay, this is the negative side, negative side, negative side, negative side. So like this, like this, like this. And then like this. Don't mind mine. You understand? You join this, you join this, you join this, then join this, join this, join this. And also know that all these panels, this one is we are making use of the VMP now. This one is 20.85. Sorry. Each panel is 20.85 volts and 9.11 amps. Each panel. Each panel. 20.85 volts, 9.11 amps. 20.85 volts, 9.11 amps. 20.85 volts, 9.11 amps. You got that? So now if you connect in parallel, the voltage still remains the same, 20.85 volts. That will be what we call, yeah. But you are adding the current. Are you getting it? The current will be added. So if you add the current, it means let me reach out to my calculator. It means if you are adding the current, you're having 9.11 times 4. So you are having like a 36.44 amps. So that would be the output if you connect in parallel. Are you getting it? So it means if you connect in parallel, you will get this voltage and this current. When you connect in parallel, the voltage remains the same, but the currents are added up. So I'm using an MPPT controller. I can decide to do this. Do you understand? My MPPT will do justice, and you know that there are different levels of charging. We have floating charge, we have absorption, we have equalization charge. Getting it? So all these things, the MPPT will do justice to it. And if I'm not connecting like this, I can decide to connect two in series, that is to have two strings, and then do a parallel connection at the end. The MPPT will know when your battery system requires more current and when your battery system require more voltage. It will do justice to that. I mean, intelligently, the MPPT controller does that. So for this design, I would say just use an MPPT. That's what I would say in my design. Just use an MPPT. And for that battery, are you getting? Let me ship this in before I end this slide. For that battery also, it is discovered that, or it is accepted that you must have at least 20, you must add at least 10% of the amperage of the battery to come down and charge your system. I have a 12 volt 220-ish. Are you getting it? So 10% of 220 ish will be what? I think that should be 222. That should be like 220 times 0.1. So it means you must have at least maybe 22 amps coming to charge your system. See what we got. 36. So we are still in order. So let's do this, and then we believe that our system will function properly. Thank you for listening. Do take your time to watch the first, the second, and then this third video. And if you have any question, I would like to go over it in the next video. Thank you.